So let me start by saying that I have no ties to any of these companies, just for an example. Well, brand loyalty can be very strong. So strong that customers who buy Coca-Cola strongly dislike Pepsi-Cola, or the other way around, of course. And for some other people, it might seem that these drinks are indistinguishable. Well, in a world where one half of the people drinks Coca-Cola and the other half drinks Pepsi-Cola, it will be very surprising to see someone who drinks both of these colas. And this is then exactly the kind of anomaly I will focus on in this talk. So it's not one of its qualities that makes this guy an anomaly, but it's the combination of the factors that defines this anomaly. So the title of my talk is Beauty and Brains, Detecting Anomalous Pattern Co-Occurrences. It's joint work with Gilles Vreken and Arno Siebes. I'm Roel Bertens. And the title comes from another example. So there are many beautiful people in the world, also many smart people, but I don't see a Nobel Prize winner often win also a beauty contest or something. So let's just imagine that someone who's both very beautiful and very smart is more rare than what we would expect from the number of smart and beautiful people. So again, this is an example of the type of anomaly that I'm focusing on. So I'm looking at transaction data. You can see the simple market basket data example. I will define the type of anomaly that I just introduced, how to identify it, and I will show you some examples as well. So what's an anomaly? We call a transaction anomalous if it deviates from what we expect, considering the whole data set. And I will now quickly introduce three different classes of anomalies. Two are well known, and the third one is the one that I just introduced in my examples. So a class 0 anomaly is, I call it the class 0 because it takes 0 patterns into account. It just looks at the transaction length of your transaction, and we define the score that can be interpreted as the number of bits you need to describe the transaction length of this transaction given the whole set of all transactions. So it's this negative logarithm is just to transform it from a probability into the number of bits. It's not very interesting, so I won't focus on it anymore, but we built on these classes. So the next class of anomalies is the class 1 because it takes patterns into account. It basically looks at the amount of regularity that you have in a transaction. And it scores each transaction based on the probability on that transaction. Again, the negative logarithm makes it so that you can interpret it as the number of bits you need to describe this transaction. Some approaches to find anomalies in this way are OC3 or Comprex, and they basically look at how to compress each transaction and given a set of patterns that is representative for your whole data set. And the better you can compress your transaction, the more regularity it contains, so the less likely it's an anomaly. So transactions without any regularity are more likely to be an anomaly. I won't focus on this class as well, but I will show you that this new class that I introduced gives you different results or new insight, new anomalies that you won't find using approaches to find these class 1 anomalies. So the class 2 anomaly is a transaction that contains 2 patterns who occur less likely together than what you would expect from the supports of both patterns individually. it's strongly based on the principle of lift. So it compares the actual and the expected probability on the co-occurrence of these patterns. And it looks at the combination of each pattern X and Y from a set S. And then it scores not these patterns, but a whole transaction based on the most unlikely combination of patterns in that transaction. Yeah, I hope that's clear. So the first question is, which set S do we need to use? So if the set S is very large, then we need to look at many, many combinations of patterns. So for example, if we look at all frequent patterns, then this will quickly become a very difficult task. As you see, that I created some synthetic data sets, just random data, and I planted some patterns in there. And you see, if the number of planted patterns grows, this pattern set S, if you consider all frequent patterns, that's the red line, the baseline, quickly grows. And also the time to compute then the scores for your transaction also quickly grows. So we need a smaller set, but we don't want to lose information. We don't want to miss patterns that will give you anomalies. So closed or non-derivable frequent patterns reduces the size of this set, but not by enough. You can sample patterns from this big set, but it's very difficult to choose the sample size, and maybe we get unlucky and miss interesting or important patterns. So we chose to use CRIMP or SLIM, which are two algorithms that basically make a summary of the set of all frequent patterns. So these summaries are mostly like hundreds or thousands of patterns instead of maybe millions or even more. So they are compact representations of the whole frequent pattern set, and their properties are that they are both so they give a complete view of the set of all frequent patterns. Of course, we need to test if then we can still capture anomalies using this smaller set compared to the set of all frequent patterns. And that's this figure here. So in this random data, we also made sure that the combination between two of the planted patterns only occurred once together in a transaction. So that was the anomaly. And it turns out that both approaches, although using the SLIM pattern set is much smaller and faster, always rank this anomalous transaction right at the top. So we don't lose this information using this smaller pattern set, but we gain much in performance. All right. So how to use these scores? Well, I would like to amplify that these different classes always should be regarded complementary. So it's not that this new score is better than the others. It's just an extra score. So it's also nice that the score also gives you an explanation of what's wrong or what's different for this transaction, because it shows you which patterns are responsible for this score. And if you want to, well, in the end you get a ranking of transactions. Each transaction gets a score. And well, we have some approach. We first use Bootstrap to approximate the distribution of the normal scores. And then based on Cantelli's inequality, we can choose a threshold based on the false negative rate and this one we have to choose to see which transactions we will classify as anomalous or not. But let's not focus too much on this. So on synthetic data, we got very good results. And we also saw that state-of-the-art, these class 1 anomaly algorithms did not find these anomalies, but using this class 2 score, we did find those anomalies. But of course, synthetic data is not very interesting as well. So we also looked at some real data sets. For example, the adult data set, it's about people's age, education, etc. It was used to predict someone's income. And the top-ranked class 2 anomaly was someone who had female sex, but was also identified as a husband, which is very likely a mistake in the data set, which is of course also an anomaly by definition. It can be very useful to identify these mistakes in data sets. At the bottom I show some figure to see how significant this this transaction was, where we generated bootstrap sample data sets with and without this top rank transaction, and we recorded the highest anomaly score for each data set. We did this 1,000 times, and then you see that the highest score, the distributions are like significantly differ, and this then must be the result of this highest scoring transaction. The zoo data set, it's 17 attributes describing over 100 animals. Well, you can see in the picture already that this looks like a very strange animal. It's the platypus, and the explanation of this anomaly was that it's the only mammal that lays eggs in the data set. Well, also sounded reasonable to us, so I think a nice example. Another one, this is a data set with presence-absence records of 121 mammals. So for each location, it records if each species lives there or not. And an anomaly in this data set can be interpreted as this red area. In that red area, both species occur both, and only there they occur together, and in all the other regions they don't occur together. So it might be interesting for domain experts, might not be interesting, but it just shows different types of anomalies for different data sets. So to conclude, well, we defined this new type of anomaly, which wasn't identified by other methods, so it's an extra type you can look for. We showed some steps how to quickly identify them in your data, and we got some nice results, I think, on both on synthetic and real-world data sets. So that's it. Any questions?
Thank you. Very interesting. Questions? I actually have a question to start off. Have you tried to use this method to actually cleanse data sets which have irregularities in them? And how has that performed if you have tried?
Oh, yeah, that's a very good question, of course. I think this could be a very good tool. So to use this score to find mistakes in your data set and then clean the mistakes. I think with anomaly detection, it's always up to the data miner what to do with your anomalies. Sometimes it's a mistake, sometimes it's an outlier, sometimes you just want to leave them in. I think in the first talk we saw it's more about understanding the anomalies so that there are not anomalies anymore. So yeah, definitely a good tool for it, yeah.
I've used low lift in the past in retail supply chain data sets to detect category killers. Like when you promote one item on sale, it really kills a lot of others. Usually you think you put something on sale and it increases revenue totally, but it has some ripple effects. So I've looked for the ripple effects in the past by looking for the low lift outliers.
Questions? This will be our last question, actually.
So in the lift calculation, maybe I didn't understand fully. So there was only X and Y. What if we have more than two? Like if there is three factors like X, Y, Z?
Yeah. Yeah, that's interesting. Of course, but that will be an extra step. So this score only looks at combinations of 2 patterns. Yeah. So if you want to look at even 3 or more, then you need to make another score even.
So then we'll take 2 at a time, and
Yeah.
then we would have like for each thing we would have 3 scores. Then what do we do with the 3 scores then?
Yeah, so it doesn't. So you will have to think about how to apply this. So I don't have an answer for you yet. But it will be the next step. But it will get complicated because then you think, okay, and I want 4 combinations between 4 or 5 patterns, and of course you see that the search space becomes only bigger and bigger if you look at higher number of combinations.
Yeah.
But yeah.
Cool.
I don't have an answer to that yet.
Do you have a paper published on this one?
Yeah.
Okay, cool.
I can